In this video, we'll take a look at stereoisomeric relationships and looking at several problems where we need to determine if the following pair of molecules are enantiomers, diastereomers, or if the compound was achiral to begin with. It could be meso or just otherwise achiral. So let's get right into it. The first question is asking just to determine the stereoisomeric relationships between the following pairs. So each question is going to have two molecules and we're going to have to relate them by stereochemistry. So to do that, the best approach that I've come up with is simply determining how many chiral centers are present and then if what's the absolute chirality at those centers, so namely R and S. So for this molecule, we have only one chiral center, and it's right here. Recall that chiral centers must have 4 different groups bound to them in order for them to be chiral. So we look at this center, the 4 different groups are a hydrogen, a CH2OH, a CO2H, which is a carboxylic acid group, and then an NH2. So that is the only carbon in the structure that has 4 different groups. If you look at this carbon, for example, this carbon is bound to 2 hydrogens. Those are the same, so therefore that is achiral, and you can do the same for the others. Okay, so now we've determined our chiral center. Now we need to determine the absolute configuration, which is R and S. So to do that, you need to use the Kohn-Ingold prelog rules to prioritize the different substituents that you have, the different groups. And the Kohn-Ingold prelog rules simply say that the highest atomic number or the highest molecular weight, I've seen it both ways, but the trend is the same. So either way, highest atomic number or highest molecular weight will have the higher priority amongst the groups. Now, the important thing that a lot of students get confused here is it is the first point of difference. So what that means is you really should go about assessing priority systematically. So you should compare the first atom that is bound to your chiral center. So in our 3 groups, we have carbon, hydrogen, another carbon, and a nitrogen. So among those 4 different atoms, nitrogen has the highest atomic number, the highest molecular weight, so that is going to be the highest priority, and there's no ambiguity there. It is clearly higher priority than the other carbons. Now, in the case of the carbon, there is a tie here. There is a tie between the 2 carbon groups, so you have to determine amongst those 2 carbon groups, the tie, which one will have higher priority. And this is where the first point of difference comes in, because now you have to go to the next atom in the structure. So here we have a carbon, and this structural feature looks like this. Right, this carbon, this dash here, this bond here is bound to this starred carbon, the chiral carbon. So the CO2H is bound to 2 oxygens, but again, in Kohn-Ingold prelog rules, we count multiple bonds to the same atom as if it was bound to multiple additional numbers of that atom. So in this case, we would treat this carboxylic group in Kohn-Ingold prelog rules as if it were bound to 3 oxygens, where the double bond counts as if that carbon is bound to 2 oxygens. Okay, so now that is clear on this one. Now if we compare it to the next carbon, the other carbon that it's tied to, this carbon is bound to 1 oxygen and 2 hydrogens. So without much ambiguity here, we know that this group here must be 2 because it is bound to additional oxygens where the other carbon is only bound to 1. So the group with multiple oxygens is higher priority than the one with 1 simply because it has a higher atomic number there in its totality. So the first point of difference would be comparing the hydrogen to the oxygen, as we have 1 oxygen that are still tied, and then the next atom would be the additional oxygen versus the hydrogens that we have in the lower priority. So that is all to say that this group down here would be the lowest priority. And then, or the lowest amongst the ones that we need to concern ourselves with, because the lowest possible priority is the hydrogen. And when the hydrogen is in the back like this, our problem solving is a little bit easier. So how I go about this is first you should determine how the structure appears. So determine R and S based on the way that it looks. So in this case, we have 1, 2, 3 like this. That appears to be R, right? And this is very important. It appears as if it's R. Appears to be R. Now, the hydrogen is in the back. So when the lowest priority is in the back, or in other words, it's a dash, then the absolute configuration is what it appears to be. So in this case, that's why I mentioned that it's relatively easy, because it appears to be R. There's no ambiguity here because the hydrogen, which is the lowest priority, is in the back. In that case, it is what it appears, which is R. So this structure is R. Now we can move to the next structure and then determine the relationship between the two. So since we already determined our groups, this is the exact same structure, different rotational state, could be an enantiomer. We need to then prioritize again, but since we've already done it, like I said, we just, nitrogen is 1, this is 2, this is 3, right? So this appears to be S, and again, I think you should think about it in this way very deliberately. It appears to be S, right? It is going counterclockwise. However, the hydrogen, which is our lowest priority, is in the front. When that is the case, you have to switch what it appears to be. So the actual answer is R. Because the hydrogen, which again is our lowest priority here, is in the front. When that's the case, you have to switch. It appears like S, so we switch it to R, so it's R. So now you just compare the two absolute configurations. We have R and R. That is the same. So these are the exact same molecule. They are identical. There is no difference. They are not enantiomeric pairs, because remember, enantiomers will have all of their chiral centers will be opposite absolute configuration. So if this was an enantiomer, you would have an R for our one chiral center here and an S for the other one. Diastereomers, by the way, are situations in which you have multiple chiral centers, so at least 2 or more, and one of them is different, but not all of them. So like, for example, if you had a diastereomer would be possible if you had a structure that was RR, and then its pair would be RS. That would be an example of a diastereomer. So, but here they're identical, and this was more or less a trick question. Okay. Next here we have another structure. So first let's determine again the number of chiral centers, and then we'll determine the absolute configuration at each one of those centers. So first one that could be chiral is this carbon here. And this carbon is bound to a chlorine, that's one group. It's bound to this whole thing here, this CH2, CH3, CH3, and a methyl group on the left. So those are all different, and there's a hydrogen, of course, that is not shown, that's in the back. So that is a chiral center. Then this one might be chiral. We have to go about determining if it is. We have a CH3, a CH3, and then this whole group, and again a hydrogen in the back. The two CH3s, which are methyl groups, are identical. Therefore, this other center is not chiral. So I will not star it to avoid ambiguity. So there's only the one chiral center where the carbon is bound to the chlorine. Okay, and then we can go to the next structure. It's exactly the same here, just rotated. All right, so let's go about solving this. Are these diastereomers or enantiomers or the same molecule? So again, to do that, first you need to determine the absolute configuration at the chiral center. So we need to determine our priority by Kohn-Ingold Prelog rules. And we have chlorine is our first atom, and 2 carbon groups and a hydrogen. So the chlorine is clearly the highest priority because it is bound, it has a higher atomic number than both the carbon and the hydrogen groups. So now we have a tie for the carbon groups, similar to the last question. We have a methyl, so that's a carbon bound to 3 hydrogens. This is a carbon bound to 2 hydrogens, and then another carbon. So the first point of difference is the carbon versus one of those hydrogens. Carbon wins, has a higher atomic number. So this is group priority number 2, and the methyl here is then number 3, and the hydrogen, of course, is the lowest priority. So this appears to be R, because it's going clockwise. The hydrogen is in the back, so it is actually R. Again, I keep saying the hydrogen most of the time the hydrogen is going to be the lowest priority, but there are cases where you can have like a methyl group or something that's not a hydrogen be the lowest priority. So to be most accurate, it is when the lowest priority is in the back that you don't have to switch it. Okay, now the next structure has kind of thrown us off here because we want to compare specifically this chlorine, this chiral carbon to this chiral carbon. It's not so bad here because this other carbon that appears to be chiral is actually not chiral. Again, it's kind of a trick. So we just want to compare the chirality at the chlorine containing the carbon bound to the chlorine in both structures, and we're not interested in the other carbon. So with that, then the highest priority is the chlorine. Next is this whole group, and then the methyl. So this appears to be S. The hydrogen is in the back, which is the lowest priority. The lowest priority is in the back, so it is what it appears. So it is actually S. So in this case, we only have one chiral center. When you only have one chiral center, if the two molecules have opposite configuration at that chiral center, in other words, that is, all of the chiral centers are opposite configuration, that is an enantiomeric pair. So these two are enantiomers. Now, a question that's commonly asked about these things is, would you expect this pair to have similar, identical, or different physical properties, such as melting point, boiling point, like solubility, things like this? So in this case, whenever you have an enantiomer, they are mirror images of each other. They may not appear to be like that in this case, but again, these bonds are moving and they're freely rotating, these carbon-carbon bonds, so you could rotate this molecule in such a way that it would appear to be clearly a mirror image. Since that is the case, since they are just enantiomeric pairs, they are identical physically. They have the exact same like connectivity and things along these lines. They would be named the same, except for the fact that you have the different R or S, and you can only detect the difference in R or S when you subject that molecule to plane polarized light and observe the rotation. And enantiomers will rotate plane polarized light in different directions, even though they have all of the other identical properties. So what that tells us is enantiomers have the exact same physical properties. I'm not actually sure if this is called a physical property, but the only difference at all in how you can tell that you have enantiomers present is the rotation of plane polarized light. If you have a pure enantiomer separated out from its pair, it will rotate light in one direction, and the other pair will rotate light in a different direction. Now, for diastereomers, that is more than often the case that diastereomers will have different physical properties like melting point, boiling point, things like this, so they're easier to be detected. And then, of course, structural isomers will have different features because those are totally different molecules. They have different connectivity. All right, let's take a look at the next set of questions here. So here we have cyclohexanes that we are comparing in their chair structure. Again, we are just asked to comment on their stereoisomeric relationships. In other words, are they enantiomers, diastereomers, or something else? So to do this, again, you want to determine how many chiral centers you have, and then what's the absolute configuration at those. Now, you need to keep your head on a swivel, though, because in this particular case, and in many of these cases, you could be given a pair that has no stereoisomeric relationship, which is the case here. Because notice we have 1,2 binding and 1,2,3 binding. In other words, the carbons that bear the substituents are completely different in the two structures. You can visualize this by putting this in their like planar representation. It's perhaps easier to see. So if you're unfamiliar with this, I can briefly describe this quickly. So here we have the OH is going down, it's equatorial down, so I draw that as a dash. It's down relative to that carbon there, the dotted line that I just drew. And the bromine is equatorial up, which is why I drew that as a wedge. So this is 1,2-trans cyclohexane. Now, so I can write that for you, 1,2-trans cyclohexane. Now, if you look at the next one, you have 1,3 trans cyclohexane. And now this of course is an alcohol and a bromine. So if you want this to be most accurate, I'm abbreviating here just because we're trying to talk about the relationships here. But if you wanted to name this accurately and completely, it would be 2-bromo. Well, it's still trans, of course. Put that out front. It's trans 2-bromo or I guess 1-cyclohexane hexanol, OL for the alcohol. Okay, but regardless, that's not really the point of this question. The point of this question is, are these stereoisomeric relationships or not? So since we have the 1,3 substitution here, these are totally different, right? We have, first of all, axial up. So this is going to be a wedge, and then equatorial down at the 3 position. Again, relative to wherever the carbon is. So that's why I say equatorial down at the 3 position, axial up at the 1 position. So this is 1,3 substitution. So this is a totally different structure. It has different connectivity because the carbon bearing the bromine is a totally different position in the ring. So these are structural isomers or constitutional isomers. Those are the same thing, different terms for the same thing. Now, whenever you see this, they're going to have different physical and chemical properties. And when you hear chemical properties in general, that's in organic chemistry, that's at least talking about the reactivity, the types of reactions that they'll undergo. They'll be different because the structures are different. So that is the main takeaway here. These are structural isomers. Structural isomers will have different physical and chemical properties. Okay, here we have another structure. This is now a cyclopentane with 5 carbons. And again, the question is, are these stereoisomers of one another? And if so, what is their relationship? So again, you want to identify what is the chiral carbon, if there are any. The one that could be chiral is this position here. However, this carbon is not bound to 4 different groups. And there's a couple ways to visualize this. Kind of depends on the person for what makes the most sense. But the thing I like to go to first is symmetry. If you were to cut this molecule in half along the line that I just drew there, you would put this group would be the same as this is the same as this, so those are identical groups. It's as if that carbon is bound to 2 CH3s. Now, in other words, if this is unclear, you can also go about this in my systematic way that I showed before when the groups are different. And how that goes is you look at the first atom that's bound to the group. So you have a carbon, you have 3 carbon groups and a hydrogen, right? So the hydrogen is clearly different, but then you have all these ties. So you have to go about assessing amongst the tie groups, are they actually different? So we have a carbon bound to 3 hydrogens. We have a carbon bound to 2 hydrogens down here, a carbon bound to 2 hydrogens down here. These are the same at this point. Carbon 1 and 2 are the same. Carbon 3, let's call it, this is clearly different because it has 3 hydrogens and not another carbon. So those are the same. So then you have to keep moving together, like at the same time, so you're comparing at the same position. So here you want to move now, let's call this carbon 4 and carbon 5. Right, so now carbon 4 and 5 are also CH2s bound to another carbon. So those are the same. So then you would coalesce on top of each other, right? You would move now to the opposite position. So if you went to the next spot going from the right, you would end up at carbon 4 and you'd end up, or carbon 5, and you'd end up at carbon 4 if you went from the left. And those are now again equivalent. So if you kept going, you would end up at the exact same spot. So that's another way really to visualize that the symmetry is present. And since the symmetry is present, that carbon is not chiral. And as such, we don't care if the CH3 is a dash or a wedge, because that's simply a rotation, a different rotation state. If you rotated this molecule, I guess it would be 180 degrees that way, like if you were to flip it like this, you would get to the wedged methyl would become a dashed methyl. But that doesn't change anything. because there's no chirality, so it doesn't matter. There's nothing on the ring to create dissymmetry. So if you rotate like that, if you put this carbon down here, it's indistinguishable from the other one. So because of that, these are identical structures. They are just conformational isomers because, again, we look at molecules at a snapshot on a piece of paper, right? Remember, the bonds are vibrating and rotating, so they're dynamic. They're not static like we look at on a piece of paper. So the conformational isomers are essentially the exact same molecule. The picture that we took is just at a different point in time. We're looking at them at different rotation states, but they're exactly the same. Any experiment you do with them is going to have exact same physical properties and like melting points, boiling points, things like this to characterize the compounds, and they're going to be exactly the same. So no stereoisomeric relationship. All right, here we have a new set of questions. This is now the same question, really. It's just a larger group of structures. So we want to determine the stereochemical relationship between all of the pairs that are feasible in this structure. So again, the best way to do this is to determine the number of chiral centers that you have in your structures, and then determine the absolute configuration at each one of those chiral centers and compare them to one another, all of the possible pairs, to determine if they're enantiomers, diastereomers, or just identical. So to do this, first we need to recognize how many chiral centers we have, and in each of them we have 2. They're here and here. And again, that is due to the fact that we have 4 different groups at those carbons. We have a bromine, a CH3, and then this like whole thing down here, and then the hydrogen, of course. And you can do the same thing for the other. So now you want to determine the absolute configuration at each of those centers. So to do that, we use Con-Ingle pre-log rules once again. So the bromine at this, if we're looking at this center up here, bromine is going to be the highest priority. Then we have a carbon, a CH3, and a carbon bound to a chlorine and some more stuff. So again, at that first atom, there's a tie, but this carbon down here is bound to a chlorine, whereas this carbon is only bound to additional hydrogens, so that is lower in priority, the one bound to hydrogens. Okay, so now this appears to be R. But now we need to remember what the Fischer projection is actually showing. The Fischer projection shows a carbon with the horizontal are wedges and the vertical are dashes. So the lowest priority is the hydrogen, which is on the horizontal, which is on a wedge. So therefore that carbon, whatever the chirality appears to be, it is the opposite. So this one is actually S at that position. Right? It appears to be R. The hydrogen, which is the lowest priority, is in the front, so we actually draw it as, it is actually S, rather. Okay, now let's look at the next chiral center. So the one at the bottom here, this we have a chlorine bound directly to a chlorine. That's definitely higher priority than the 2 carbon groups. Up, we have a carbon bound to a bromine versus a CH3. The carbon bound to the bromine is definitely higher priority. And then the methyl group, of course, is last. So this appears to be S. However, again, the hydrogen is on the horizontal, so we have to flip it. So this is actually R. So this group here is S and then R. Okay. Now we can move to this next carbon, and here's a little like trick that can help you solve these problems much faster. Is if you're confident in the first one that you solved, you can go about it systematically in such a way that you don't have to solve the absolute configuration at every possible chiral center. You just relate what is the difference between the two, the one that I solved and the one that I'm looking at now, and it can help you do this quickly. So what I mean is, anytime you switch 2 groups of a chiral center, you invert the chirality. So we switch the bromine and the hydrogen here in this structure, which would then make this from S, it now becomes R. Right? And we can check this to make sure that this works by doing the absolute configuration. But you don't want to do that every time if you can avoid it, because it takes some time, right? So here we have a bromine, and then the carbon bound to the chlorine is 2. This methyl is 3. This appears to be appears to be S rather. The hydrogen is in the front. The lowest priority is in the front, so it's actually R. So our little trick did work. And then if we look at the bottom carbon, nothing has changed, so that one should still be R. Which again, you can check for yourself, but it will be the case. So here we have R and R. Okay, now if we do the same thing to the next one, this one, it's kind of up to you how you want to compare here, but you could use the first or second one, to compare to the third molecule. So here we have a bromine on the right. This bromine is on the left, so we have to invert. So this one is R. Here we have the chlorine on the left now. This we have to invert is now S. Right, so this is R, oops, used the wrong color, but this is RS. Okay, now if we move to the next one, we need to compare where the bromine is. The bromine is on the same position, it's on the right as it was in the first one, so this is S. The chlorine is opposite, so this is also S. Right, so this is SS. Okay, so now, using our definitions of enantiomers and diastereomers, diastereomers are when you have 2 or more chiral centers and one of them is opposite, but not all of them. Because if all of them are opposite, it is an enantiomer. So what we should do here then is look at what we have. So if we have, this is 1, 2, 3, and 4. So let's do diastereomers first. So 1 and 2 are different by only one position. 1 and 3 are different at both positions, so those would be enantiomers. 1 and 4 are different at one position, so those are also diastereomers. Okay, now if you move to 2, 2 and 3 are different at one position. 2 and 4 are enantiomers. They're different at both positions. And if you move to 3 and 4, they are different at one position, which is also diastereomers. So the diastereomers group you would expect to have different physical properties because these are not related by rotation or mirror image, so they are completely different structures, and as such they will have different physical and chemical properties. Now, what about the enantiomers? There's 2 pairs here of enantiomers. We have 1 and 3 because S switched to R switched to S, so 1 and 3 are completely opposite at both configurations. And then 2 and 4 are also opposite. So these you would expect to have the same or extremely similar physical properties. And then to check if these are all the possibilities, you should just go through and see if these are all the pairs that you can have. So you can have 1 and 2, which we have, 1 and 3, which we have, 1 and 4, have down here, 2 and 3, we have here, 2 and 4 is present there, and then 3 and 4 is the last pair, which is present. So we have 6 possible pairs here, they're all accounted for, and that is how you solve this problem. All right, here we have another question that we are asked to determine the number or the stereochemical relationships between all the pairs in this group of 4. So again, to do that, you want to determine the chiral centers that you have at each structure and then determine the absolute configuration that is present. So this one's particularly hard because we have Fischer and skeletal structures. So we'll have to determine the absolute configuration at each type of group at least. Like we'll have to do it in the Fischer and the skeletal. We can't do our little shortcut to compare the Fischer to the skeletal because they're different representations. So unless you can convert the two in your mind, which I cannot without a molecular kit, so you would have to actually go through each individual carbon and determine the absolute configuration. So let's do that. So first we have 2 chiral centers in both of them. Now we need to determine a priority. So fluorine is the highest priority here. Then we have carbon bound to a bunch of carbons and a carbon bound to hydrogens. So the carbon bound to a bunch of carbons is higher priority. This appears to be R, right? It is rotating clockwise. So is it actually R? Well, the hydrogen is in the front. The lowest priority is in the front, so it is actually S. Okay, let's move to the next carbon. The next carbon is bound to a carbon bound to a fluorine, carbon bound to another carbon, and a carbon bound to only hydrogens. So the carbon bound to the fluorine is highest priority because, again, I can go through this a little bit more slowly. You have a carbon, carbon, and carbon, so that's a three-way tie. Then you have to go to the next atom. The next atom for this one is two hydrogens and a carbon. For this one is a carbon and a fluorine and a hydrogen. This one is just bound to other hydrogens, so the one bound to the fluorine is higher priority. Then the one bound to the carbons is next, and then the methyl is last, and the hydrogen, of course, is the lowest. So this appears to be R as well. It's going clockwise. The hydrogen is, again, in the front, which is the lowest priority, so this is actually S. Okay, so that's that one. Now let's go through the next structures, which are now skeletal. So again, here's our two chiral centers. So we need to determine the configuration at those two centers. So this carbon is bound to a fluorine, and then the whole carbon group here, and a methyl. This appears to be R. The hydrogen is in the back, so this is actually R. Okay. Now if we move to the next one, we have this whole carbon-containing group here. We have a carbon bound to another carbon, a methyl group, and a carbon bound to a fluorine and another carbon. So the carbon bound to the fluorine is highest, the group bound to more carbons is second, and the methyl is last. This again appears to be R. However, the hydrogen, which is the lowest priority, is in the front. So this one is actually S. So this one is RS. Right? Now we have to be super careful at the next one because they've shown the structure in a slightly different representation than we have seen it. So we had the fluorine, the carbon fluorine group at the top here. We had it at the left here, but now it's on the right, which means that we want, if we're going to try to compare in order that we're listing this, we need to put the fluorine group first, which means we need to determine this chirality at the right, far right of the structure first before we do the one that's in the middle if we want to compare S to R and S to S, you know, for example. So yeah, you just want to be very careful, make sure you're paying attention to where the carbon is that you're actually comparing, which in this case it's on the far right. So fluorine is highest priority, then this carbon group, then the methyl. This appears to be S. The hydrogen is in the front, so it's actually R. So this one will be R. Okay, now let's do the one in the middle. So we have, again, the carbon bound to the fluorine is highest priority, then the ethyl group, then the methyl group. This appears to be S, but the hydrogen is in the front, so it is R. And now the fluorine is back to the left, just to make this as confusing as possible. So the carbon is bound to the fluorine, that's highest priority, then the carbon group with more carbons, and then the methyl is last. This appears to be R. The hydrogen is in the front, lowest priority, so it's actually S. Okay, and then here's our last chiral center. We have a methyl group, the carbon bound to the fluorine, and the carbon bound to other carbons. Carbon bound to the fluorine is highest, then the ethyl group, then the methyl group. This appears to be R, but the hydrogen is in the front, so this is actually S. So when we compare these groups, we do exactly what we did last time, where we look at the number of different or opposite configuration we see at our two chiral carbons. So here, let's start with diastereomers. So 1 and 2 are diastereomers because they are different at only one position. 1 and 3 are enantiomers, so we cannot, they're not diastereomers. 1 and 4 are exactly the same, so there's no stereoisomeric relationship there. 2 and 3 are also diastereomers, and 2 and 4, which is the same, since 4 is the same as 1, 1 and 2 and 4 you would expect to both be diastereomers. Okay, now enantiomers. We have 1 and 3, as they are opposite at both positions, and then 1 and 4. And then lastly, identical are 1 and 4. So excuse me, this was 3 and 4. 1 and 4 are identical. Right? 1 and 3 are enantiomers. 1 and 4 are identical. 3 and 4 are also enantiomers. Yeah, that's right. All right, here we have our last question of the video. So we are asked which of the following compounds is or are meso. There might be more than one. So as a quick review, meso compounds have 2 or more chiral carbons, and their absolute configuration must cancel. Which means that one would be R and one would be S. So in other words, this absolute configuration must canceling means that there is an internal plane of symmetry. So let's go through this. So all of these structures have 2 chiral centers, so they could be meso, they meet that minimum requirement, but only 2 of them have mirror planes or internal mirror planes. So, and I'll demonstrate that at the end. So first, let's determine the absolute configuration at each center and show why the mirror plane is only present in 2 of them. So our 2 chiral carbons are this and this. So this carbon is bound to a methyl group, a carbon bound to 2 carbons, and a carbon bound to 1 carbon. So the carbon bound to 2 carbons is highest, then the carbon bound to 1 is next, then the carbon bound to hydrogens, the methyl group, is last. This appears to be R. The hydrogen is in the back, so it's actually R. Okay, let's do the next one. The next one is bound to a carbon, again a methyl, and then a carbon bound to 1 more carbon, and a carbon bound to 2 carbons. So the carbon bound to 2 carbons is highest, carbon bound to 1 is next, the methyl is next. This appears to be S. The hydrogen is in the back, so this is S. So this meets our absolute configuration must cancel, so this one is meso, and it has an internal mirror plane present here, where if we split that molecule in half, the 2 groups on either side are exactly the same. This is not the case for 2 and 3, which are trans. Only the cis, the 1,2-cis cyclohexane is the 1,2-dimethyl cis version cyclohexane is actually going to be meso. So again, we can illustrate this with the next problem. If you look at the absolute configuration at both of those carbons, so this carbon is bound to a carbon that has 2 more carbons, that's highest priority, then the carbon bound to 1 more carbon, and then the carbon bound to only hydrogens. This appears to be R, but the hydrogen is in the back, or excuse me, the hydrogen is in the front, so you have to switch it to S. And next one, we have 1 here, 2 here, 3 here. So this appears to be S. The hydrogen is in the back, so this is S. We don't have the canceling of configuration, and also you can now see the mirror plane is not present because of the geometry is not the same. They aren't cis, so those would not superimpose on each other. So then this one must be RR. You can check this for yourself. And this one is then SR. It is the enantiomer of 4, and therefore 1 and 4 are meso. All right. And that's all I had for this video. I hope you enjoyed and learned something from it. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic suggestion or anything like that, please feel free to leave it in the comment section down below, and I will make a video on it as soon as I can. So I hope you all have a great day, and I'll see you in the next video.